let's get going for class then. You and fade out. Okie dokie. So let's see, administrative stuff. So I graded your last homework, so by and by they're all pretty good. I think the only time I really took off points was if you didn't implement something, if you did something wrong, or if you didn't give me enough detail on like a couple of the Q&A type things. Um, so that's pretty much, I was pretty, I think more or less pretty generous, I think, on that one. Um, but overall, I think everybody did pretty well. And if you had, I didn't really notice anybody that really had big problems. Like I know somebody, I think their reset function was flipped around, and I think one other person might have had collision detection issues, but by and large, everybody seemed to get that, so I was pretty happy with that. The only like real question that was on that one was the collision detection question. Let's get some more light in here. And that was basically, I wanted you to kind of think about how we could optimize collision detection. And it's just drawing less particles and just drawing less objects is not really a good answer. It's, let's apply some distance functions to see who is nearby. Or I like the ones where people are talking about like partitioning up the canvas into regions. And if you're in zone 1, then you get checked with other members of zone 1. So stuff like that's kind of what I was looking for. But I think if you at least made an effort, I gave you some points for that one. Other thing that we've got going on, so I will, depending on how far we get today, my plan is to either put the next homework up today or Thursday, kind of depending. So I will be getting round 2 of the vaccine tomorrow night. And based on how I reacted to round 1, I'm anticipating that Thursday may be a different type of class. I'm not sure what it's going to be like. But if I'm knocked out, I will probably give you an out-of-class lab to do. If I'm fine, we'll see. Just keep an eye on your emails for an announcement. I'll know tomorrow night, basically, what's going to happen. But I'm expecting to get knocked on my ass, basically. So just depending if that happens, I'll have you work through the assignment. And the next assignment is actually going to be about, oh, it feels good. I get to be superhuman now, right? Isn't that the what happens with the vaccine? But the next lab is actually, we're leaving my third arm. Ooh, is that what I get? That'll be helpful. I can play some of those old 90s era FPSs where you need like 10 fingers plus an extra 20 fingers to, move your mech around the screen or something like that. But our next assignment, we're actually going to go into some of the, oh, I've been missing that. They're so tasty, I don't get the N64 controller hate. If you swapped hands, that's, it wasn't that bad. But if you've ever, I don't know if any of you have ever tried GoldenEye in the Source engine, that's, mouse aim is delightful. But the next assignment is actually going to be, I don't think I have it in this tab here. Okay, there we go. Stop. Next lab is over here. We're going to be checking out some of the other libraries that are out there. So basically what it's going to be doing is I'm going to have you play around with one of the other 2D and one of the other 3D libraries. And I've got some stuff for you to do with that. But we're leaving Angel and Schreierland. We are checking out Babylon in 3 and Pixie.js and Phaser. And you're going to see how much fun it is with a real library behind you for WebGL. So we'll do that. And then after we get through that aspect, we'll do Blender and then Unity. And that I didn't want to do Blender on a day where I'm going to be horribly out of it. Other libraries, we can get through that pretty easily. But Blender's a beast to get through. Lots of demos and lots of clicking the correct box. But that's about where we are at here. I guess I should mention too, your next lab is also going to have term project work on there. So if you haven't started anything for your term projects, which is fine, I really haven't pushed you to yet other than to think about it. Your first task will be to do 2 things on your term project and tell me what they are and what you have to do next. So start thinking about that. Details will be in the assignment for that deliverable as well. But this is about where we ended up. So we were talking about the look at function. We were talking about how we basically can generate our matrices for our current transformation matrix using some of these library API calls that we have. So if you remember, calls to translate, calls to rotate, so on and so forth, they're basically just generating matrices that we are going to sling along to our shaders, which will then be in charge of actually applying them. And if you need a refresher on that, because I think towards the end of the last class, probably was starting to get pretty dry. So here I'm in perspective. I guess we were in, let's look at ortho since that's what we were doing before. We were generating an eye function, so we're basically generating the eye of our camera. And we have, basically some fill in the blank type formulas for this. We're generating our model view matrix with our eye, what we're looking at, and then which way is up. We're generating our projection matrix, which in this case is an orthographic matrix. We have some things that we will be talking about today and what these are going to be. And then we're just passing them along to our shaders. So this GL uniform matrix 4V, that goes right into our shader here. So projection times model view times position. And again, I'm going to keep saying this over and over again. These are all post multiplied. So it's V position times model view, that times projection, that equals your new position. And hopefully what you're kind of getting out of this and what, maybe we can at least appreciate is that switching from perspective to orthographic to isometric, any of our different views, all that is changing our projection matrix. So here we're generating an orthographic perspective. We can call some of the perspective functions to generate those matrices, and that's what we're going to be getting into today. All this is populating a matrix. We don't care in WebGL exactly what it is as long as it fits that 4x4 construct. Anything can go into these two and we'll be happy. So position our camera, position our objects, make a projection from that. And if we look at our demos here. So again, chapter 5, these are the different ones that we have. Here's our orthogonal. If I increase phi, this is that I that we have, right? We're basically changing how this matrix is being populated. And it just kind of looks like we're, kind of swinging the camera around, basically around the y-axis. If we play around with theta, then we start changing. Let me go right to the exact line of code. Theta is also going into our eye. I thought theta was being used elsewhere as well. No, it's just in our eye. But again, these are basically dinking around with our camera. This is populating our model view. And then our Z's and our R's, we're dinking around effectively with our clipping plane. So you can kind of see the effect that these variables have. And this isn't intended to be, a tetrahedron here. This is intended to be, the corner of a cube. It's just everything else is out of the clipping plane that we have defined. Very, very handcrafted at this point, obviously. We are going to see in the other libraries how much easier it actually can be. And if you're kind of trying to think about where libraries fit on the scale of complexity, what we're doing here is kind of very bare bones, right? We have these helper functions which kind of help us fill these matrices, but we don't have a lot of the extra fluff to really make it easy for us as programmers. You have just the raw WebGL basically. libraries are going to add a layer of abstraction where you can just say define a camera and have it follow an object, right? You don't get an appreciation for what these matrices are doing there. But you do have to understand the math, which is kind of why we're going through this. Anyway, so that was all orthogonal. That is our default projection. What we're going to kind of do now is we're going to talk about our perspective projections as well, and our parallel projections, and we're going to kind of go back and forth with some of them. So if you get lost or confused, please let me know. What we had talked about before was basically that model view matrix. So that was step one. Now we're going to talk about the projection and getting those different views of our objects, those, perspective or, any of our axonographic views. So what do we have here? We have a homogeneous coordinate representation. So this is our multiplier that we're going to apply to get a default orthographic view. Now, our default view volume here is that we are going to leave z as nothing. And I guess another point that I should mention, this is kind of what I've been talking about, by converting everything to more of a standard transform, we get this nice behavior where our shaders are always going to look like this. So this is our pipeline. Right, we kind of broke that down into multiple steps, but really this is our straight up, at least the vertex aspect of our pipeline. So going back to our slides here, if we want a default orthographic view, this is the matrix that we're going to apply. Again, this is the default setup, where we have basically our camera oriented orthogonally looking at an object. Our center of projection is at the origin. Our projection plane, by default, it would be at the origin as well. We are actually going to shift the camera back a little bit just to make life a little bit easier equation-wise. And that's not going to mean a whole lot to you right now. But when we start looking at some of the equations, we're going to see that basically z has kind of slid down this way. So let's say that this is the object we're looking at, centered at xyz. We have a projection plane, xp, yp, zp. So basically this is kind of where the camera was, and we see that we've actually moved its frame back a little bit. So you would see like a positive d translation of the camera. This is just going to simplify things for us. It's going to look a little bit more complicated, but really it's actually going to make life easier. So we have perspective is the first thing we're going to look at. How do we calculate a perspective matrix? This figure kind of looks a bit wonky. I will say that it's kind of hard to break down if you're just looking at this. This is the exact same figure that we had here, just with less shading and less axes, basically. So we have a figure here in the xz dimensions, and we're going to slide our camera in the d direction. And if we take this to the y and z, so basically this is like your top view and your side view of something. We see that we're sliding our center projection in the d direction again. And we're just basically shifting things along. And all this is doing is we're setting our z to be some value d, which is how far we're bringing it along in the z direction, right? So think of your camera. I'm going to use my phone as a camera here. So we're at the center, we're at the origin, we're pulling it back positive d, meaning that it's looking in the negative direction for z. What this is doing matrix-wise, and your fill in the blank for the matrix, z is set to whatever that d is. I think we typically set it to 1. Our x and our y's are going to be divided by z divided by d, and that is how we're going to populate our perspective matrix. This particular set of equations here is our divider, and it's why things actually look farther away. So that's that whole notion of perspective, right? Center of projection, we are looking out. The farther away things get, right, they actually look like they're getting far away. That's what these dividers are doing here. So if we know that, how do we apply a homogeneous coordinate form? Again, this is our multiplier. So we have an identity matrix here, right? 1, 1, 1. We're going to set our w to 0. We're going to set this location to 1 over d. And what's going to happen here is that we get basically kind of our nice exact, XYZ, and then our W position is 1, because remember, we like this value to be 1. By introducing this divider here, we're basically ensuring that happens. Okay, so if our W is not 1, we have to divide by whatever that W is to get back to this homogeneous coordinate form. So again, this is what we're calling homogeneous coordinate form. This is just that divider, and we're getting our perspective equations from that. A lot of very high-level logical math. Bear with me here, we'll take a look at it in WebGL. What this means for us is that we're calling the ortho function. Right, so if we take a look here in ortho.js, we see this ortho function. I can do console.log p matrix, and this is my local copy, so I have to remember to open my local one. I need to open my local one, please. This is what his local folders look like. Look how messy they are. Everybody pointing left. All right, so it's going to keep going forever because I'm logging it every single frame. But we're actually going to see 1, 1, negative 1, 1. So this is what we're generating for this particular orthographic setup. And this is based on, again, it's not going to be exactly like what we see in the slides here, because we're actually setting these a little bit differently for this particular camera. I guess I probably should have made that a little clearer. In this case, the left is negative 1, right is 1, top is 1, bottom is negative 1. That's what we see here. Left, so negative 1, 1, negative 1, 1. Our near and our far planes are kind of the interesting thing to set here. I guess I should take a step back. Perspective and orthogonal, where it's a little bit, parallel versus perspective. When we talk about perspective division, we're actually going to be calling other functions. It's going to be this guy. So, sorry, didn't mean to jump ahead there. Ooh, that's exciting. I assume we're all on the same page here, right? Yeah, confusing. Takeaway is effectively we're just generating matrices based on what we want to see. So with a perspective, we're going to have a divider on the bottom, right? If we're going orthogonal, we're getting parallel lines, right? So that's our parallel perspective. And you see that this view volume here is a parallel, we've got parallel lines coming off. There's no center of projection. So the interesting thing for us when we define our matrices here is we need to define the close plane and the far plane. And that's going to be what we're drawing. And this near and the far, it's measured from the camera too. So if we've pulled our camera back here, when we're setting our near and our far planes, it's the distance from the camera, like at this location, to that point, this location to this point. And that's kind of what we're setting with this. And when we set this in WebGL here, near is negative 1, far is 1. So basically what we're saying is that this would be like a negative 1. And then, sorry, I keep flipping back to the wrong one. And then z equals negative far. So it'd be also, it'd be 1. So we have this object, and I closed the wrong window. Oops. So that's our ortho. Let's also take a look at our MV matrix. Yeah, I'm clicking the wrong thing. Sorry. Basically, it's important to define just kind of the bottom left corner and the top right is kind of the way to think about this one. With the perspective, we're actually going to have two different functions which we can call. So if we want to generate the perspective matrix, and again, this is the projection aspect of it. So which view are we kind of projecting here? Ortho, we care about these particular points. Perspective, we're going to do one of two things. So let me get this to be full screen again. We're either going to call the frustum function, which is just a truncated pyramid. So you kind of see that's what this volume is right here. It's not a true pyramid because we're lopping off the top because it's a, it's a set of planes. It's not a point. But we are still kind of drawing similar things. So we care about the near point here and then the far plane here. And we're going to set the points that we need in frustum. And we get to see that in, well, this one's FOVY. This one's also FOVY. I thought I had a frustum open. All right, bear with me here for a second. Yeah. Come on, click the right thing. Find in files, frustum. Should be in chapter 5. Do we not have an example of this one? Of course we don't. I could have swore that I had one. Oh well. So that's kind of the interesting thing here too, brief diversion aside. So when we're generating a perspective view, we have the option to call frustum, and we also have the option to call FOVY. These are basically two different functions which are going to get us a perspective style of drawing. Now here, we're going to call it very similarly to ortho, so left, right, bottom, top, near, far, left, right, bottom, top, near, far. Function feels very, very similar. Again, still measured from the camera, except now we have the center of projection here, and based on how we're defining these points, you're going to get a perspective instead of a parallel projection. But it's kind of hard to get the view that you want with frustum. So in this particular view, if you want a good perspective image, oftentimes this FOVY function makes it a little bit easier. And in this case, we only care about, so effectively this FOVY, this is going to be an angle from the top and the bottom planes. And you kind of see it here. So we have like these rays coming off from our center of projection to the front plane. Whatever this angle is what we're going to put in FOVY. And this angle specifically is going to make it a little bit easier for you to get the view that you want, if that makes sense. So assuming we can figure this one out, aspect ratio is just your width divided by your height, and that's the width and height of your front plane. And then we're also going to add in the near and far planes as well. So in perspective 1 or 2, we have this call to perspective, and we're using the FOVY. Now, I'm just saying these things expecting you to understand them, right? But let's actually take a look at what these are. So FOVY, hitting the right buttons, FOVY, we're saying this is a 45-degree angle. So that is what that angle is from our planes. So this is our field of view, okay? Probably understand this from games where you can slide that FOV around. Performance, that is a good question. So aspect ratio, well, in 16:9, you can have higher, I guess it depends on your resolution. It's mainly how much you're drawing on screen. I don't know that the performance would be any different for the same scene if you change the aspect ratio. Good question, though. All right, so we have FOVY, we have our aspect ratio, which we're going to calculate out from our width and our height. Our near and our far planes should just be, okay, they're a little bit different here. So 0.3 and 3, so we basically have changed the distance here. There's some separate calculation. No, not really. It's mainly just a divider. So I can pull that up here somewhere too. Yeah, so it's just canvas width divided by canvas height. It'd be an interesting study, though. I can't imagine performance would change. So with all of these, we are. I wish it wouldn't like crap its pants every time I tried to exit out. We basically have just kind of different ways of showing the user what we want. So here I'm kind of playing around with our, our various values that calculate the eye of the camera. And they're very finicky, I should mention too. I think it was perspective 2 that had the sliders, yeah. Let's open up perspective 2, not to ramble too much here. Interesting thing, so the shaders don't change, just multipliers here for us. I'm looking at perspective 2 now, which is handling sliders instead of button clicks. Everything else is pretty much the same though. So we're getting our perspective function, FOV, aspect near far. Our model view matrix, we're figuring out what the lens of our camera is, and we're looking at something. And our looking at something is basically this theta and this phi kind of aggregated. So if we screw around with theta and phi, we get kind of the same behavior that we've been seeing. If we change our field of view, you kind of get what you know from, at least hopefully what you know from playing around with video games where you can change that FOV. Basically, you can see more, right? Or since we're looking at things front on here, kind of looks like it's getting bigger and smaller. Now let's, but these ones are kind of fun to play with because you can kind of see if you do them like one at a time, what the actual impact on a scene is going to be. Let me refresh this here. Let's play around with our aspect ratio. You can kind of see things just distorting based on our various values here that we're playing around with. Radius, so this was again part of the eye of the camera calculation. But let's try and move this guy over here. And then we can also play around with our near and our far planes. So let's make this, yeah, here we go. That's a good view. So what I've done here, and I'm just kind of playing around with these sliders, and honestly, perspective 2 is a good one to play around with as well. I'll drop this in the chat so that you can see it. But we get some extra values to play with here. So aspect is our aspect ratio, field of view. Again, that goes into our calculator for the perspective view. Theta and phi are going to be part of your camera lens along with radius. But the new ones here are these near and these far planes. And what these are is where we are setting the front and the back of our field of view, or sorry, of our perspective here. And if we start shifting that front plane backwards, we can actually cut our object open in half because the front of this thing is now outside of our clipping volume. And what WebGL is doing is it knows that, okay, now you can see these things because the front of it's clipped out. I was just basically kind of playing around with near and far and trying to get it to such an angle that we could start slicing into it. So that front plane is kind of moving back a little bit. And if I, let's see, let's make that bigger. I think if we go all the way up, it's just not going to show anything. So what I did here was I made the front plane and the back plane the same. So there's nothing, there's no clipping volume. But this is a fun one to play around with, at least I think it is. Okay, so and yeah, I'm basically going to leave some of the calculations here. is things to kind of check out. I'm not going to hold you to understanding exactly what a perspective calculation for the eye is versus a orthogonal view or something like that. These are all things that we can really just look up, I feel anyway. Everything else is the same though. So draw arrays, request tandem frame, uniform matrix. These are all identical, perspective, orthogonal, parallel, whatever your view is. All you're doing is setting a different projection matrix. If you want that parallel view, call ortho instead of perspective. Okay, so with that now, we're going to start talking about actually clipping. And what we're doing here is we're going to take everything that we've done and we're going to normalize it down. So basically everything that we are doing projection-wise is going to be converted into the default view volume. And what that is doing is it's taking our scene and shoving it inside that cube that we know is our clipping volume. And again, by normalizing things, we can just treat every matrix the same, which makes life a lot easier for you. And why is that the case? Again, you don't care perspective, orthogonal, isometric, trimetric, dimetric. You don't care. It's just a matrix. It's being clipped regardless of what type it is. It's just up to you to set what that clipping point is. All right, so just to kind of remind ourselves what clipping is, let's say that we have a scene that looks like this. We have some strings. Clipping hides everything outside of that clipping volume. And again, for us, it's a 2x2 cube. All right, so at this point, we've done our model view transformation. That's, again, move objects around, move our camera around. This is basically one matrix, and that's comprising translations, rotations, all that stuff that we did a couple lectures ago. Projections, what we just talked about, call perspective, call ortho, whichever view you want, that's our projection. After that, we're going to do our perspective division, which is going to bring everything down from our nice 4x4 matrices into 3D matrices. And after that, we're going to clip against our cube, because we're now in 3D land, and then we're going to project into our 2D plane, which is going to be your screen that you see here. So with this, I mentioned this last time, the goal of this whole pipeline is to stay in 4D as long as possible. All right, so you don't want to lose information before you need to. Once you get beyond 4D, or from 4D into 3D, we start losing information. Right, we get to 2D, we've lost depth. At this point, we're hoping that we have drawn everything properly. What I kind of skipped over though, is there's this non-singular aspect to our model view and our projections. There is an inverse to them, so we could technically go backwards if we needed to, right? We can invert the matrices if we need. And we saw that before, where we say move the camera or we moved an object's frame from the origin off to some point. Or we took it from some point, moved it to the origin, rotated it, and then moved it back. And we're calculating inverses that way. But once we get past that and we normalize, which is just another matrix multiplication, we're going to clip against that cube. The projection that we are doing helps out with this. So with our matrices that we're generating with ortho with perspective, basically what we're doing is we're going to take this volume that we've created with ortho, and perspective is going to look similar, right? It's just going to be slightly distorted. We're taking this and we're mapping it to our 2x2 cube, right? So this is 2x2, so this is -1, +1, -1, +1, 2x2. This is getting squished down, and that's what normalizing is. Everything that we have might be different shapes and sizes, but it's all getting squished down into a 2x2 cube. So what happens with that then? So let's say we are in orthogonal land here. We're going to move its center to the origin of our clipping volume, and then we're going to scale it. So these two functions here, so if you remember, T is translate, S is scale, just normalization mathematical functions for doing this. And we're going to make it look like this, and that's going to take everything inside it and clip it out for us. If you want to know what the actual matrix looks like, so we have this S times T, so again, translate times scale. We're basically just taking X, Y, and Z, normalizing, and then we have our dividers here in the fourth column. And what this ends up with is a matrix that looks like this. So we have this matrix times this matrix, and that is our general projection. I said before that we're doing a generalized projection. Basically, it's this M orthographic would be M perspective times our projection here. Right, and that's going to bring us into our clipped cube. So that has been orthogonal, that has been perspective. Hopefully that's not too confusing. One thing that we didn't really talk about was oblique projection. So we talked about our orthographic views, our orthogonals, right? Isometric, diametric, trimetric. We talked about perspective. We kind of skipped over oblique. And when we talked about the classical viewing, that was you have, like a picture that you take and then you slide your camera around to get another view of things. Only special cameras can do that. What this projection is going to be, if you want to represent this, and again, you probably may have a reason for doing it if you wanted to show this type of a view, well, it's just a shear. And we talked about shear as one of our transforms way back when we started talking about matrices. So all this is let's take an orthogonal view and add a shear onto it. Because again, we're pulling things in opposite directions. And all that means to us is that we're bringing cotangent into the equation for our matrices. All right, so these figures are going to look a little bit wonky. Basically, what we've got here is that instead of our usual degree of projection going kind of, from top right to bottom left, we're basically reversing it here and pulling things apart. So you kind of see this angle theta here lines up with this particular plane, and this angle phi is with what we want our oblique shape to actually look like here. So this again, top view, side view, theta, phi. And all this really means is that we're defining another matrix. And those two angles that we want, whatever the degree of obliqueness is, are going to factor into this matrix H, which we're going to call our shear matrix. So we have an identity, and then we have a negative cotangent of theta, negative cotangent of phi, and there you go. That's all we need. If we want to take that and turn it into a projection matrix, take this, multiply it by our identity matrix for an orthographic view, and then we have a projection. And that is your projection, like your PV matrix equals shear. This is oblique. If you want to generalize it even more, toss on that ST for scaling and translating, and then we have our general projection. So basically, just to kind of summarize here, I've got this M orth. Again, that's back here. This is our homogeneous coordinate system here. So our orthographic view, multiply that by your shear. That's your perspective. And we also have an equivalency here too, which is kind of nice if you want to go that route. We can apply P, so our general case directly, or we can multiply the shear by our orthographic view. So basically, we can apply things in two ways. We can use that general case that I showed you, or the specific shear matrix. That's kind of all that's really getting at there. Let's see. So without going too deep into a bunch of gibberish with other matrix types, pretty much everything left in these slides is a repetition of what I've been kind of going over here. What I would like to do is, yeah, everything's going to be the same. I'd like to actually start dipping into some of the other libraries so that we can kind of move on here. Now, if you want to get some practice with this, this isn't going to be a graded thing. You can take one of the rotating cube functions and merge in the calls to ortho. Basically make it an orthographic view. And if you remember, I think it's chapter 3 had those exact spinny cubes. Oh no, it's chapter 4, sorry. So basically, if you want to play around, take one of these and then check out, either one of the orthogonal or one of the perspectives. Try to merge some of the code together. So again, if we look at the cube, I don't know, I'm looking at this instead of the code. It's still going to be, well, it'll be a little bit similar. Here it's spinning around, but we can actually apply these angular matrices to a different projection as well. So you can concatenate in different projections. But if you want to play around with that, I would recommend checking it out, if you have time. Any remaining questions on here? I know this is probably confusing without a lot of extra practice. I guess when in doubt, check the brain melting. Perfect. Really all it boils down to is which function are we calling here? Are we generating a perspective matrix or are we generating an orthogonal matrix? It's just different matrices that we are filling in the blanks for. And the blanks are really just, okay, where do you want the front plane? Where do you want the back plane to be? All right, I do kind of want to get into some of the other libraries so that we know what we're doing on Thursday, though. So I would say peruse the rest of those slides if you want to get some more detail on the symbolic math for the matrices. But I think you should all be relatively okay with that at this point. Let's take a look at one of the other libraries, or some of the other libraries. I don't remember why I made slide 1 a cassette here. But I've got some links for you in here. Now, with graphics on the web, there are some very well-known frameworks that are out there. Again, the one we have been using has been to really enable the book examples and give you as much of an appreciation for what's going on behind the scenes as possible. This library that we have been using is not the most user-friendly, and I'm going to guess that you're all more or less seeing that at this point, right? We kind of understand that you're basically doing the C version of graphics, whereas everybody else is off doing, C# or Java with all the extra stuff added on top of it. These libraries here are very, very helpful for getting up and running, and we can play around with perspective and orthogonal views with basically 3 or Babylon. So 3 and Babylon, these are 3D libraries for WebGL. Phaser and Pixie are 2D libraries. Phaser and Pixie tend to be video game oriented too, mainly because pretty much everything you do in 2D graphics on the web is probably going to be more or less game oriented. So they're really good with things like sprite management, where a sprite is some object that's like a video game character. They may have animations or velocities or things of that nature, collision boundaries, things like that. 3 and Babylon are more high-level 3D frameworks. You can do games in them. You can also do simulations. You can do animations, whatever you want to do for 3D. They're very, very powerful. So they're just abstractions for us. They are a level of indirection to make your life as a programmer easier, right? Generating these matrices that we've been doing in the Angel and Schreier book, they have some of these helper functions to make life easier. This takes it a step further. And that whole vertex by vertex thing that we have had to suffer through, and now you should suffer through it at least once in your life, it's going to be basically obfuscated for you. So I'm going to go through these slides here momentarily. I love this guy's website for slides. I think it's pretty nifty. But there's also a Medium article I've got here too if you want another perspective on it. But let's start out with Three.js's representation. And I should mention too, Three and Babylon are not necessarily interchangeable. Like they're not going to have the same function calls. They're separate libraries, so keep that in mind. Typically, you'd pick one or the other. You're not going to mix and match both. I'm not used to having a tea bag in my tea. Getting slapped in the face with a big wet tea bag, it's not pleasant. All right, so in three, so this is where we're going to start. We've been defining yeah, it's semi-intentional. See if I could get a laugh from anybody. Yes, Archer. So if you want to define a vector, it's a vector 3. That's our vec3 that we've been using. And if you want to define it, it's something, const your variable name equals new 3.vector3. So what we see here, we are basically using this library. We're going to call its various, functions, various parameters. It's going to be prefaced with a capital 3. So that's how we reference their API. We can also have, and this is going to be new for us, a box 3. So if we're going to generate an object, we can generate a bounding box for it. So if you generate, say, a sphere, we can put a theoretical box around it, and that's going to be, maybe a collision boundary. Maybe it's a hitbox, or maybe it is just for orienting axes. If we want to define a box, we don't have to draw 500 quads. We can just say box equals box 3. And then our vect is going to be effectively where its origin. Now, this box is going to be world aligned, at least initially, meaning that whatever your frame is, your origin plus your axes, it is aligned with those axes. So think of a 3D cube, plop it on top of a XYZ set of axes, that means world aligned. Right? It's not like rotated until you say rotate. So to give you a visual here, because me doing this with my hands is probably not super helpful, especially on camera, let's say that we create a sphere. So this is 3.sphere, I believe. We have a 3D sphere. We didn't have to draw the triangles. We didn't have to calculate the triangularization here. Three.js does that for us, which is one of the things where I said it makes life a hell of a lot easier. But let's say that we want that bounding box now. We can generate something that looks kind of like this, and it's up to you if you want that to be visible or not too. We can basically create it from some pre-existing object. So let's say we created this sphere elsewhere. Well, let's set the box around that object, and now it's an axis aligned. And you can kind of see, right? So the, here's our X, here's our Y, here's our Z. It's aligned. We also can define some visible things, which is very, very helpful. All we have been doing in basic WebGL land is colors, gradients if we're feeling frisky, and that's about it, right? Here we can also define materials, we can define material types, we can make it reflective, we can put the specularity, basically all those different materials that you see slapped onto 3D objects, very easily do in here. So just keywords, hopefully this is memorable. Geometry, we're defining our shape. Topology would be what that shape is. I'm not dealing with that here. Material is going to be our appearance. So geometry and material. This is our vertex and fragment shaders from what we know so far. So if I wanted to define, say, a cube geometry, so I'd say new 3.box geometry, 2020, X, Y, and Z is a cube with length 20. And it would look somewhat like this. What if I want a sphere? Well, here's my sphere. Radius of 20. I think it's a radius of 20. So some basics for you, and then I'm going to go into this other guy's stuff basically, because he's got a much better set of slides than I do. We're going to import the Three.js library. So whereas before you had MV, MV2, um, whatever the other one was, here we're just including one library call. You don't need MV or MV2 anymore, just 3.js. And you would download this, or you would point to one of those like JS deliver hosts or something like this. Thank you. Like I said, it's good to get an appreciation for the hard work underneath it and understanding some of the transforms under the hood will help you with this too. So let's look at this guy's stuff because I like his slides. Um, ooh. So I've got the links here if you want to go through it. He also has a presentation video as well. I think he gave this at a conference a few years back. Now hopefully we can make cool things. You could make cool things before, it just would have been painful. Alrighty. So some of this I'm going to skip over. This is boilerplate that you already know. Like you know what WebGL is. You know that we need a canvas element. Here's one cool thing you can do with WebGL. So this is this guy's demo. I would recommend too, while we're talking about 3 and Babylon and stuff like this, they have a list of demos and sample projects on each of their sites. Definitely worth checking out if you want to, say, get started with one of those. Yeah, absolutely. Well, there's lots of interesting things you can do with the vehicles, right? Because metal has different sheens, you can do different colors, there's lots of angles to play with. Fun stuff like that. But all right, there should be something here, I think. Why is there nothing here? Okay. Go back one. All right, so in 3JS, we can render to WebGL. We can also render to HTML5 or SVG. Basically, you're not strictly limited to WebGL with some of these libraries. So something to keep in mind if you want to like support other browsers or other devices where a WebGL context just isn't feasible. You can do that with some of these libraries. Before we were only doing WebGL. Not as big of an issue anymore, honestly, but if you want to support, maybe an older system or something like that, or you want to go maybe a little bit more old school with HTML drawing. But what do we get out of this? We have scene management. So everything we've done so far has basically been a single scene. You can't easily swap from triangle bouncing around the screen to points. Oh yeah, I'm not trying to crap on basic C code. It's just spinning ASCII donut thing. We'll have to check that out. Do you have a link to that one? Perhaps find that. I don't remember seeing that. I guess the point is though with these libraries, I'm not trying to say you should use this. Like if you want to do straight up raw WebGL, you are more than welcome to. And you can get much better performance out of that usually because you have direct access to everything. When you go to libraries like this, you're offloading the effort to the library and hoping they optimized properly. Just something to keep in mind, but you're going to spend a lot more time doing the basics if you're going straight up C and OpenGL or something like that. But in here, we can very easily manage scenes. We can play with multiple cameras. We can very easily load 3D models. So let's talk about this one since we're doing Blender next time. If you wanted to load in a Blender model in pure straight up WebGL, you would have to understand A, how to parse one of those object files or model files, and then you'd basically have to be able to import that into your scene, understand what all those materials are. And for some of this, it just becomes much easier to use a library, honestly. Lighting, we haven't even touched on yet in straight WebGL, but that's going to play with our materials. maybe we're going to have some particles or things like that. So this is the Three.js website as of a few years ago, at least. It still looks pretty similar. But here's basically a list of all the examples that you can get up and running in WebGL. Let's see.
Here on the left is a spinning ASCII donut, and on the
that's
right
cool.
is a donut-shaped C code by Andy Salone that generates it. Now with syntax highlighting.
Oh, that's cool. Oh, syntax
I
highlighting.
recommend you check out a donut. Then this ASCII
Oh God. Okay. That's worth watching over later, I think. Can't believe I just clicked a video that one of you just blindly sent me without even previewing it off screen. Shows how much I trust you. I'm gonna regret this one, aren't I? Oh, maybe not. These ASCII things are awesome, but really okay, so yeah, that's our classic scene. So, out of clapped. This is the last video I'm clicking, by the way. So this is super cool. I don't think this is that tricky though. So like if we know how to render a scene, um, basically you can correlate different values with different ASCII codes. That's pretty much all that's going on here. Yeah, it takes a crap ton of understanding, but basically we're just mapping down to ASCII key codes with various values here. Definitely, definitely cool looking. I'm gonna have to watch this offline. C++ ray tracing demo. Fun stuff. I really considered it. Missed opportunity. So this is the Three.js example page. So let me pop over to 3js.org. Looks pretty similar. But in here we have a bunch of examples. So like here is a cloth in the air. Here's little Tokyo. Handling skeletons, camera views. And so, so also nice, orthographic and perspective view. Here's our ortho, here's our perspective. Then you can actually kind of see what we talked about last time with the clipping volume and the viewing plane, the far and the near plane, center projection, angle of field of view angle. So this is perspective. Here's our orthographic. Nice parallel viewpoints here. But Three.js website, you can get the code for all of these too. They're all up on GitHub, which is very, very nice. With this one though, so here's our spinning cube. This is kind of that boilerplate code that I had on the slide. How do we generate this now? This is kind of the interesting thing for you. Yeah, that I should have had that in my slides because I like that. So we're going to define a scene. We're going to define an aspect ratio. We're going to define a camera and a renderer. And then we're basically just going to add that on. So let me get everything in here. So a scene basically is going to contain everything that we want to show in the current location. Actually, I think the tree is going to be more helpful here. So this is getting a little bit deeper into like high-level graphics pipelines. A renderer is basically going to spit out information. And you kind of can see in something like this how every object type depends on every other type. Like in a scene, we're going to have a camera, we'll have a bunch of meshes, we'll have a light source or multiple light sources. Our mesh is basically just a list of vertices, maybe a list of faces. That's going to become some geometric object like a sphere or a cube or something, whatever we're defining. These are going to get hooked up with the material. So maybe it's an image, maybe it's a color, maybe it's nothing and we're just leaving it as see-through. But these are going to kind of combine in something called a mesh for, 3JS. So vertex fragments combined, we get a mesh. And that's going to go into a scene. Can you have multiple scenes? Absolutely. Can you have multiple meshes, multiple light sources? Try to have, maybe one active camera at a time. But we basically have pretty powerful API calls here. So scene, camera, render, we're defining early on. Camera, kind of the thing we already talked about earlier in WebGL. We're defining a perspective camera. Right, so I don't remember exactly what the particular attributes of the 3JS perspective camera is. Let's look this up right quickly. So, okay, field of view, aspect, near and far. So it is the same thing. Just wanted to make sure. So, field of view, 75 degrees. Aspect ratio, near, far. Pretty much the same calls that we made in our book library. You could make this an orthographic camera as well. Let's look up ortho. So width minus 2, or width, sorry, divided by -2. Interesting. But effectively it is the left, the right, the top, the bottom, the near, and the far. So again, the same kind of values that we'd shove into the other API. Now, our cube. So this guy that we are spinning here, we're defining this cube, right? Geometry, it's a box. It's material. We have a normal material. Normal actually has meaning here. And the cube is going to be a mesh made out of this geometry and this material. So basically define the object, define what it looks like, call it a cube, add it to the scene. There we have a cube. Instead of defining each vertices, pushing that down with our, let's see, in the last example, we had that edge list or the face list where we're defining like the quads, right? And that was pushing down all the triangles. Here we're letting 3JS handle that for us. We're putting the camera back by 5, and then this render function actually looks pretty similar, right? So render, request animation frame. We're going to tell the renderer, so this is a different thing here, we want this object, this WebGL renderer, to render our scene with our camera. And if we wanted to switch scenes, we would basically change what we're rendering. And then this is going to animate. So rotation.x plus 0.1, rotation.y plus 0.1, get something that looks kind of like this. A little bit cleaner, honestly. Ooh, a spam text message popped up. So, if you want to start playing around with 3D on the web, a lot of bit cleaner. Yeah, absolutely. This idea of a scene graph, this is going to be a little bit more common too with some of the more powerful tools that are out there as well. All right, so you can get something nifty like this. What's this? Well, it's a group. We can have objects have parents. They can have children. We can do lots of crazy things. So this is basically one cube that's being treated as multiple. We can do transforms. A lot easier, at least. So here's its position.x equals 0, -100. Can scale it. You should be rotating. Okay, there we go. Some nice math libraries for radians to degrees, degrees to radians, depending on what you're looking for. You can rotate it around the circle. Or we're just setting its position x, position y based on what we know of the unit circle. We kind of did this before when we rotated things, right? We played around with the cosine and sine for x and y. Here we're still applying the rotation as well. Oh, it's not a cube anymore. Now it's a pumpkin because we imported a pumpkin library. Again, we have different cameras, so here's our perspective. Oh, I forgot, these are interactable. I keep forgetting about that. So here's our perspective camera. Different fields of view. Different plane. Do an orthographic camera. And what I think is honestly one of the more fascinating things with this, and honestly, I love this view because you can see exactly what all of these objects are, or sorry, what all of these attributes are. There is this notion of an orbit control, which is great for 3D. So I'm just kind of clicking and dragging here. When you add in a camera, you can tell it to orbit. I'm just kind of zooming in, zooming out. What if I want that? I just call orbit controls on the camera that I want to control. So if you want to kind of zip around your scene, just call orbit controls and the camera that you are using. It makes life so much easier. You know, if you wanted to do this in WebGL, you'd have to get the quick event. You'd have to get the direction that your mouse is moving, right? We're going to have to redraw our scene, move everything around. It's kind of why I kind of glossed over some of the more deeper matrix things because we're going to do something like this. What can we do with our camera? Pan, zoom, rotate, set various distances, min and max angles. Orbiting's fun. All right, so we got a few minutes left here. Let's see how far we get. So we have different geometries that we can set to, not just a cube or a sphere. You can get a box, you can get a sphere, you can get a cylinder, you can get a torus. Predefined API calls for you. So there's your ASCII donut right there. Draw a torus and set its material to be whatever ASCII mesh you want to generate. With materials, we finally get to play around here. Thing to keep in mind, we talked about this, 3, 4, 5 lectures ago when we watched the Disney animation. Light will have an impact on your material. So here we see a nice flat shading, very matte looking shading, kind of a cartoon looking shading. These are things we can just directly apply. So there's your basic, here's your Lambert, Phong, standard, tune, normal. Again, there's not a lot of hard extra stuff you have to put in there. If you want that Wind Waker look for your game, mesh tune material. There you go. You also can see the normals coming off of it too if you want. So if you have a shape where you need to see like the normal lines being drawn off of it for whatever reason, you can have that set as well. I also have some parameters. Do you want it looking flat? Here is actually the faces of this polygon. So flat shading false, nice kind of smooth-ish sphere. If you look at the edges, you can kind of see it, but with the number of vertices specified for this particular sphere here, it looks like a fairly smooth object. But you turn on that shading, okay, here's what it actually looks like polygon-wise. We can get the normals coming off of each triangle. Again, the normal's that perpendicular line. You can display it. You can even show each triangle if you want. Kind of looks like a pinhead type of thing. We basically have some different properties we can play around with. How shiny do you want it? You want it to be a wireframe. You can go the classic battle zone look. Transparency, get that too. One of the fun things, which I'm going to guess a lot of you will appreciate, we can do UV mapping. So take one of your textures and slap it onto your object. So here is our standard map projection. We've got a sphere. We're going to make a UV map based out of that. All this means is we are mapping this image onto something like this, and it's going to be slapped onto our sphere. So then you get sphere. Oh, nice. Well, how do we do this? UV is so cool. UV is very cool. 2 lines of code. So load a texture and slap it on there. You can also get a normal map if you want to do some bump mapping too. So if you want to go that route where it's not just a flat surface, add some actual hills and valleys to your thing. You can do your normal mapping as well, your bump mapping. Specular map for lighting. And we actually have something that looks like a real globe here, right? Take this and apply it to any textured surface. You're typically going to have a color map, specular map, and a normal map. This is your bump map, basically, where you have definition, how shiny are things, what are the colors, and you have your, in this case it's a globe, but it could be anything, right? So this is exactly what this sphere looks like here. So it's a falling material. Here's its color, specularity, shininess. These values will play around within Blender and you'll get a feel for what they actually are. All right, a couple more minutes. We have lights. So we can have a directional light, meaning that we have a light source with a direction. You can change the lighting color, which is great. What if you want a point light, meaning you just have like a light source with light going out in all directions? Well, we get that too. It's a point light. Spotlight, so we basically have like a perspective kind of thing coming off. Multiple lights. Import models. Pretty straightforward calls to load things in. So here it's loading it as a JSON object. You can also use your GLTF out of Blender as well, but basically just bringing it into the system. Hey, here's 3 teapots with 3 different textures applied. Interestingly, this that you're seeing in the background here, this is just a skybox. So basically there's an image mapped onto a cube. Interactions there too. So we talked about like picking before. I love this visual, so cool. Yeah, how much? Okay, so that is the end. So this is what I wanted to show you before for visuals. All right. So point is, WebGL is super cool. At this point, we kind of got the basics, hopefully under, in a reasonable appreciation. Now we're moving into the more complicated things, and we can do some neat and interesting things with this. So the progression is going to be normal WebGL. Let's look at some libraries, look at some modeling, then we'll see where we can take it in, say, Unity or something where you even have more abstraction from the core basics. So If you want to play around with this thing, I love this demo. Because you have picking, we have orbital controls, we have textures. You have kind of a fixed image here. It's like a Doom type of enemy floating around, always facing you. So, I will see you all hopefully on Thursday. Depending on how tomorrow goes, I'll either put the homework assignment up either tomorrow or Thursday, just depends. But other than that, I will go. I wasn't able to join. No, you didn't miss anything. So your current homework assignment, which isn't live yet, will have details on your project. I guess the takeaway is I was happy with everybody's proposal. Structure it like 2 to 3 homework assignments worth of effort. Don't go all out, more of like a prototype of WebGL for you. And your next homework will have forced progress with that. These are different notes. Yeah. If you are working with someone else, I will need to eventually know that. So if you're working on a team, the scope and expectations will be a little bit higher, but yeah. I'm fine if you want to group up. That's absolutely okay with me. You should be able to do something more interesting than if you're doing it just by yourself, right? Alrighty. Well, I will see you all next time. Have a wonderful day. Enjoy the 70-degree weather, and yeah, see you soon. Yep, you told me that. And I think both myself and Professor Dulamerta were okay with that, if I recall. I don't think I saw his response, but I was at least okay with that. Anyway, see you next time. Bye, everybody.